Hi everyone, let's go through some questions on alkanes. Okay, this is compound L, assuming only monochlorination takes place, ignoring the relative rates of abstraction of different types of hydrogen. Which of the following statements is incorrect? Okay, so let's look at the first part. They say the maximum number of chlorinated products formed is 8. So I'm just going to say this. I can kick out this H and put in a Cl. Or I can kick out this H and put in a Cl, or I can kick out this H and put in a Cl, all right? Or I can even, okay, for this one over here, I can kick out this H and put in a Cl, or kick out this H and put in a Cl. They actually mean the same because it's this molecule is like symmetrical, all right? So you must be able to see that. So I'm just going to say this. I'm going to substitute a H with a Cl over here, or it could be here, or it could be here. Or it could be here, or it could be here, or it could be here, here, or here, all right? So these will give you the different number of types of chlorinated products. So let's count 1, 2, 3, 4, 5, 6, 7, 8. So this statement is actually correct. Okay, the next one, C20H38 is present in small quantities. So when they say small quantities means it's actually found in trace amount. And if it's found in trace amount, it's only found in the termination step. Okay, so I'll say this, in the propagation step, we know that C10H20 will react with chlorine radical. Okay, Cl dot, and you form C10H20, and this will be a radical. Right, you form radical plus HCl. So in the termination step, you'll realize that two of this can actually combine to form a product. Okay, you have kicked out a H already, so this must be H19. Right, this H19. So two of it will combine, right, to form the product, all right, a side product. So it will be something like C20H38, right? So which means this statement is correct. Okay, homolytic fission occurs in both initiation and propagation. We know that the initiation step will be Cl undergo homolytic fission, right? So this is what you get. So this homolytic fission. Okay, in the second, in the propagation step, actually homolytic fission also takes place. Say for example, C10H20, right? So one part of it is like, maybe I just draw this part. Okay, so in fact, how do you get this product? Okay, in fact, homolytic fission takes place. So this, okay, it works this way. So you can see that this is actually homolytic fission, right? So you actually end up getting RC dot. Okay, yeah. So this is just an example. Actually, it's like there's a H and H over here. So RCH2 dot, where this is plus HCl. Okay, so this part here is actually homolytic fission. Homolytic fission is taking place over here. So this statement is actually correct. Okay, this is the tricky part. The ratio of the primary to secondary to tertiary chloroalkanes has this ratio. Okay, so I'm just gonna show you what it means. Okay, so if I imagine there's two H's over here. All right. So this is a secondary hydrogen. This is a secondary hydrogen. So if I replace this secondary hydrogen with a Cl, this becomes a secondary halogenic alkane because this carbon has one R group and another R group. So this is a secondary halogenic alkane. All right. So if I replace this hydrogen, this over here, this hydrogen is called primary hydrogen. If I replace this hydrogen with a Cl, this becomes a primary halogenic alkane. All right, because this carbon has only one R group. Yeah. Okay, but if I replace this hydrogen with a Cl, this becomes a tertiary halogenic alkane. All right, so imagine this is a Cl now. Can you see that? Okay, so we're going to look at the primary, secondary, and tertiary chloroalkanes. All right, and see whether we get the ratio of 3:6:2. So what you need to do is you have to substitute the hydrogen with a Cl. Okay, so for primary, I'm going to label all the primary. So primary, actually, I have two hydrogen here. Primary here. Primary, this part, only these two will give you a primary halogenic alkane. any of the H's from here or any of the H's from here can be substituted to give you a primary halogenic alkane. So the number is 6. So for secondary, there are actually many, right? There are actually really many. So this part, there's the hydrogen, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So actually it's 12 over here. So any of these hydrogen can be substituted with a Cl to give you a secondary halogenic alkane. All right. Okay, the last part, the tertiary, right, is actually the hydrogen over here that can be replaced with a Cl, or the hydrogen over here that can be replaced with a Cl to give you a tertiary halogenic alkane, and the value here should be 2. So if you look at it, the simplest ratio would be 3:6:2, right? It would be 3:6:1. Okay, but this is 3:6:2, so this is actually incorrect. So the answer is D. All right, so that's how we do it. Okay, let's look at the next question, question 2. Okay, cyclopentane undergoes substitution with bromine. What's a possible byproduct? So this byproduct is always the thing that has happened, that thing is formed in the termination step. So chloropentane is like this. All right. So what happens if you form, say for example, like this? Okay, you kick out a H and form this radical, and you have another one, another of the same radical. All right. So when they combine in the termination step, this is the product. Okay, you must see a line over here. So that's why the answer is D. Okay, all these are wrong because you will not form this. Okay, you will not get this. So all these are not possible, right? Same goes for this. I don't think it's possible. All right, so it doesn't work this way. Okay, so so this is the answer for D. I just showed you how it's formed. Okay, so let's look at question 3. Which of the following is a propagation step in the formation of 1,1-dibromopropane from the reaction between propane and bromine? Okay, so let's look at all these reactions. Okay, over here this is wrong because in the propagation step you kick out the H, not a Br, but you kick out a Br. So this is wrong. For the second one, this is not propagation. Radical and radical is actually termination step. Right, termination step, right? Okay, so this is wrong. Okay, let's look at the third one. Okay, so this is actually the second step of the propagation step. So what you actually will end up getting is not this. In fact, you end up getting CH3, CH2, CH2, Br plus Br radical. So you regenerate the radical. So that's why C is wrong. So the answer is actually D. Okay, in fact, this is the first step of the propagation step. So you kick out a hydrogen and replace it with a Br. Okay, you kick out a hydrogen and replace it with a Br. Okay, so this is what you get. Then the Br radical is generated. All right, so this answer is D. Okay, let's look at the next one, question 4. Which statement about this reaction is correct? So the reaction involves homolytic fission and sigma bond formation. That is true. Okay, I'm going to show you why. So if I have to draw the mechanism, this is how it works. CH3, I'm going to draw this. Okay, so this is what happens. I can draw a half arrow here, and this is a half arrow. So the end product is actually, this is a homolytic fission. Okay, see that? This bond breaking is actually homolytic fission. And this OH, right? OH, right? It forms a bond with the other H over here. You see? So this is sigma bond formation, and then plus CH3 dot. Right? So in fact, A is the answer already. You see that? Okay, let's look at question 5. Okay, how many distinct monobrominated alkanes can be formed? Okay, so let's see. Okay, there's a CH3 here and there's a CH3 here, and these two are attached to the same carbon. All right. So in fact, any of these H's, any of them can be replaced with a Br, and then actually you get the same product. Okay, actually get the same product. Right. So I'm going to just draw what are the possibilities. So by brominated, so this Br this H can be kicked out to be replaced with BR1. The H from here, there's a H over here. It can also be replaced with a BR. So this is 2. This is 3. This is 4. This is, okay, there's a CH3 here, right? So you can kick out this H, right? So this will be, I'm going to draw it out so it should look like this. 5. There's a H over here that can be kicked out, so it becomes 6, 7, and 8. All right. So that's why for this question, if you did it properly, you'll realize there's actually 8 possible monobrominated alkanes. All right. Okay, let's look at the next part. Okay, so yeah, I'm doing all the BR here, but I'm trying to show you all those are the possible positions where the BR can be. Okay, let's look at the next question. When heated with chlorine, 2,2-dimethylbutane undergoes free radical substitution. All right, how many different radicals are theoretically possible? So you can replace any of these H's to form a radical, and that's considered as 1. Right, so I'm going to draw it out nicely. So this is actually considered as 1. All right, this is considered as 1. So the other radical that can be formed would be this, whereby you kick out the H from this carbon. All right, so there's 2. And the last radical that can be formed is this one here, which is 3. Okay, so this H that can be kicked out, so this is what you're going to get. All right, so the answer is B. Okay, let's look at question 7. Okay, let's look at question 7. 3-methylpentane. So this 3-methylpentane. 1, 2, 3, 4, 5 pentane, right? So this is 3-methylpentane. So you're gonna get 3 possible monosubstituted halogenic alkane. So what are they? Okay, the first one is 1-bromo-3-ethylpentane. So this is what it looks like. Okay, 1. All right. So that's the first one, right? The second one will be 2-bromo-3-ethylpentane, which means it looks like this. This is BR over here, right? I hope you get that. And the last one, the last one is 3-bromo-3-ethylpentane, so it should look like this. The BR is over here, okay? So these are the possibilities, right? So what is the expected ratio? Okay, in order to get the ratio is always the number of H's times the rate of abstraction. Okay, so you must know that that's how we get the ratio out. Okay, how many hydrogen can be replaced to give you this compound? In fact, if you look at it carefully, the CH3 here, and the CH3 here, right? Any of these H's, if it's replaced with a BR, it gives you this compound. So which means it's 9, because you have 9 possible H's. Okay, let's look at the next one. How many possible H's can you kick out to give you this compound? So I'm going to write down here. Actually, it could be any of the CH2, any H's on the CH2 here, or here, or here. So because all of them are attached to the same central carbon here. So in fact, this one will be 6 possible hydrogen. 1, 2, 3, 4, 5, 6. Any of these 6 hydrogen can be kicked out to be replaced to give you this compound. Okay, the last one is there's only 1 hydrogen here, right? So this is 1. Okay, let's see what hydrogen did I kick out. So this hydrogen that was replaced is actually a primary hydrogen. This one that is being replaced, right, is actually a secondary hydrogen. And this one is actually a tertiary hydrogen. All right. So primary hydrogen, I told you, right, times the rate of abstraction. For this one, since you are taking away a primary hydrogen, primary, you times 1. Okay, it's easier to abstract a secondary hydrogen times 4. So secondary hydrogen, this one is times 4. And the last one is a tertiary hydrogen, which is the easiest to be abstracted, you times 6. So if you look at it, what would the numbers be? Right, it will be 9 is to 24, 6, 18, 6, 12, 18, 24 is to 6. So once you divide by 3, this will be 3, this will be 8, and this will be 2, right? So the answer is actually C, right? So that's how it's done for question 7. Okay, let's look at the next question. Question 8. Okay, in this free, it's quite similar, right? Okay, quite similar, but so I'm going to do it very quickly. When 2-methyl butane reacts with bromine, 2-methyl butane is like this: 1, 2, 3, 4, 2-methyl butane. Consider the type of hydrogen and the relative rate of abstraction. So I told you just now, the ratio will be number of hydrogen times the rate of abstraction, okay, to give you the ratio. Okay, so what are the possible expected ratio of primary to secondary to tertiary bromoalkane? Okay, for primary, let's look at this one. For primary, it could be any of the H's here, here, or here. Okay, so these hydrogen are the primary hydrogen. All right, so I'll say is for primary, yeah? Primary bromoalkane. So once I replace the primary hydrogen with a Br, it becomes a primary bromoalkane. Okay, this is primary bromoalkane. Okay, so there's actually 9 possible hydrogen. So for secondary, it's over here. Secondary is this one, 2 only. Right, so it's 2. Right. For tertiary, the tertiary, you realize that it's actually this one over here. Use a different color. It's here. Okay, this one over here. This is a tertiary hydrogen. You kick that out, replace with a Br, you get a tertiary bromoalkane. Okay, so tertiary is, in fact, it's only 1. Right. Okay, so for primary, don't forget what's the rate of abstraction. Right, 1. So you have times 1. For secondary, CH2, in fact, they did it very nicely here. This one is times 4, and this one is times 6. So again, the ratio is 9 is to 8 is to 6. Alright, so that's why the answer is B. Alright, so this is how we do it. Okay, let's look at the next question. Question 9. Alright. An alkane acts with the molecular formula C4H10 reacts with chlorine in the presence of light to form 2 monochlorinated alkanes, Y and Z. Alright, in the molar ratio 9 is to 1. Okay, what are the structures of X and Y? So if you notice how to get only 2 monochlorinated alkanes in a ratio 9 to 1, so you must try to figure out what is the structure for X. Okay, and it's C4H10. Okay, so actually this is the structure for X. This is the structure for X. Okay, so why does it give you 9 is to 1? Right, because it's like this. Okay, if you replace any of this hydrogen, okay, so it's 9. You replace this hydrogen is 1. Okay, is that? So I'm just going to draw it up. So the 9 is to 1. So the 9 will be something like this. There's Cl over here. The 1 will be this one. So this ratio will be 9 is to 1. Okay, because to replace any of these H's and put it as Cl is this one here. Alright, so there's actually 9 possibilities. 9 is to 1. Alright, so what do they want? They want the structure X. So X is done. And Z. Okay, so Z is 1, right? So this is Y, this is Z. Okay, so let's check it out. So the answer is actually C, alright, C. So if you try to draw out nicely for Z, you can see that it's actually CH3, CCl, CH3, and CH3. So that's the structure. Okay, let's look at question 10. So the answer is C, right? Yeah. Okay, let's look at question 10. When heated with bromine, hydrocarbon C undergoes free radical substitution. The free radical is formed by the loss of 1 hydrogen. Okay, what's the structure of hydrocarbon C? There are 3 possible theoretical forms of the radical. Okay, for this question, I hope you can tell. Let's try it maybe. Okay, for this one, actually, I believe you can see the CH3. Any of the H's here, because of the symmetry, right? Any of the H's here can be replaced. Can be kicked out to form a radical. So that's considered 1. Any of the H's here is considered another one. So there are 2 actually. So they say 3, so it's not the answer. So this one, let's see how many possibility. I can kick out the H from here 1. I can kick out a H from here 2. I can kick out a H from here 3, 4, and 5. So there are actually 5 possibilities. For this one, I can kick out 1 H here, or 2, or 3. All right, symmetry, so I'm not going to do the other side. 1, 2, 3, 4, 5. So this one is also 5. Okay. Okay, how about this? Okay, this one actually, maybe I draw this out nicely. Okay, so hopefully you could see that replacing any of these H's, right? Any of these H's here, H here, H here, or H here, because all these CH3 are all attached to the same carbon. So replacing any one of them will give you 1. The second one is replacing any of this or this, right, will give you 2 because of the symmetry. And last one is replacing this one here, 3. Okay, so there are 3 possible theoretical radicals actually. Okay, if you need me to draw it out, it's probably like this. So this is the first radical. Okay, first possible radical. Okay, so the second possible radical. Okay, just for this question, I'm just going to draw 1. This one possibility. The second possible radical will be, of course, this one, CH2 dot. Okay, H, and of course the last one is actually just this radical. All right, so that's how it's done. Okay, so these are the 3. Okay, so yeah, so that's why the answer is B. Got it? Okay, let's go to question 11. In the presence of UV light, ethane and bromine react to give a mixture of products. Okay, and which compound cannot be present as in the mixture, right? So usually this, you can see from here, all these probably form in the termination step. So ethane, right? So ethane is CH3, CH2, CH3, CH3. So in the propagation step, you'll probably get this, CH3, CH2 dot plus HBr. Okay, then in the termination step, 2 of this will combine. In the termination step, this termination step, 2 of this will combine, right? And you'll form CH3, CH2, CH2, CH3. Okay, so normally you have to realize one thing. In the termination step, when you form like a byproduct, the number of carbon will always be a multiple of the original one, or your original hydrocarbon. The number of carbon will always be a multiple of that because you can only keep adding 2 carbon at a time. So if you look at this whole thing, the easiest way to look at it is this. So over here there's 4 carbon, and this one has how many carbon? 1, 2, 3, 4, 5, 6, 6 carbon. Yeah, it's possible. This one is 1, 2, 3, 4, 5, 6, 7, 8 carbon, possible. 1, 2, 3, 4, 5, 6, 7. Yeah, so it's 7 carbon, not really. Okay, so it's not possible. Okay, so if I have to show you why these can work, right, where did the 6 carbon come from? So this is the one, the radical. Okay, so this one here is the radical, and then they form a bond here first. Okay, so this was the bond formed between the 2 radicals. Okay, then after that, this will form a radical. This part will form a radical, and then combine with another one. There's a radical. Can you see that? So they'll join together, right? So actually, these 3 radicals actually were from here. 1, 2, 3. Okay. So if you look at this D, why is it not possible? This one here, and this one here. All right. So where did this carbon come from? Okay, so yeah, so this is a lone carbon. Where did it come from? So you can't tell because you must always have 2 carbon. It's always a pair. All right, so that's why the answer cannot be present, right? It must be D, really. Right? Anyway, the easiest way to do it is to count the number of carbon. Okay, let's look at question 12. Okay, which reaction is a propagation step in the chain reaction between bromine and ethane? So because it's ethane, which is CH3, CH3, you can't have this radical. Okay, so that's out. For the next one here, you are breaking this bond, right? It shows that as if you're breaking this bond, which is not possible. It doesn't break the CC bond. So this is also out. Okay, so this is actually correct. This is actually the second step of a propagation step. So what happens is the Br goes in and you form another radical. Okay, Br dot radical. So this is actually correct. For this one, it's wrong because you don't form a H radical. H radical is not formed in free radical substitution. All right, so yeah, this is probably the answer. Okay, or in fact, this is answer. Okay, let's look at the next question. Question 13. Which of the following molecules cannot be formed from the termination step? So the answer is A, because like what I mentioned, H radical is not formed in free radical substitution. So there's no such thing as H radical plus Br radical to form HBr. Okay, this doesn't happen because H radical doesn't even exist. Right, okay, let's look at question 14. Pentane was reacted with chlorine in the presence of UV light. Okay, how many monochlorinated products, including stereoisomers, are possible? So this is pentane. 1, 2, 3, 4, 5. Yeah. So how many monochlorinated? So I'm going to just draw the first one. So the first one, you can put the Cl over here, or you can actually put the Cl on the second carbon, or you can put the Cl on the third carbon, and that's it. Okay, but because including stereoisomers, you must be able to draw a chiral carbon, right? So in fact, this is a chiral carbon. So there are two isomers here. There's one here and there's one here. So altogether, there'll be 4. So that's why the answer is B. Okay, let's look at question 15. In the reaction of methyl propane with chlorine, which of the following compounds can be formed? So methyl propane is like this. So with methyl propane, you can actually form 2 different radicals. All right, the first radical will probably be something like this. So you kick out a H from this carbon, you get a radical here. Okay, you could actually kick out a H on this carbon, right? And then you get this radical. So it's supposed to be like this, all right? But I'm going to draw it this way so it's easier for you to see the answer later on. Okay, so yeah, so this is what it looks like. So let me just take this away. All right, so let's see how you get these products. So the first compound can be formed. All these are formed in the termination step. So can you see that this is your one of it, all right, and this is the other one. You see, and then that's where they form the bond. All right. Okay, for this one, you can see that this was a radical, and this is the same radical. All right, and they form a bond here. The last one is actually these are the 2 radicals. One radical here, and this is the second radical, and yeah, they form a bond over here. All right, so actually 1, 2, 3 are all possible. So the answer is A. Okay, let's run through question 16. So which rule gives the correct number of mono-substitute bromine alkanes and their relative proportions when 2,4-dimethyl-pentane reacts with bromine? So 2,4-dimethyl-pentane looks like this. 2,4-dimethyl-pentane. Okay, so they're asking for the relative proportions of the mono-substituted bromine alkanes. So let me just draw it out first. Alright, so the first one would be, I'll put the Br over here. So whether you put the Br, because these 2 are CH3, right? So whether you substitute this H here or H here with Br is actually 1, right? And the second Br can be on this carbon, and the third Br will be on this carbon, right? So let's check it out. Okay, for the first one, you can actually replace for the number 1, right? You can actually replace any of these H's, all right, to give you the first product, which means is actually 12. Okay, to get product number 2, you can replace this H or this H with a Br. So this is 2. So for the third one, right, you can either replace this H here or this H here. So it's 2. So the ratio is actually 6, 1, 1, right? So 6, 1, 1. So you can see that I drew out 3 possible mono-substitute bromine alkanes. So that's why the answer is A. Okay, let's go through question 17. All right, so the first part, say both P and Q produce the same number of monochlorinated compounds with the formula. Which pairs are possible? So I'm going to go straight to answer. The answer is D. Okay, why is the answer D? Because if you look at it carefully, we can replace any H on this carbon, or this carbon, or this carbon, and it's the same. All right, so I'm going to put in the say a Cl over here. okay, we could actually also replace any of the any of the hydrogen on this carbon, or this carbon and this carbon is actually the same thing. So I'm going to put a C over here. Okay, and we can also replace any of this, or there's only one carbon here with a H. So this is the last one actually. Alright, so this is the third possible monochlorinated compound. Alright, so yeah, 3. Okay, for this one, for the second compound, okay, we can replace this H, the H on this carbon or this carbon. That will give you the very first compound. So that will be C over here. Okay, the second possible one is this carbon or this carbon. Alright, so this is a Cl. Alright, the last one actually is over here. Okay, we can replace any of the hydrogen on this carbon or this carbon, and it give you the same thing. So this is Cl. Okay, so in fact P and Q, both of them produce 3 monochlorinated compounds each. Alright, so that's why answer is D. Alright, the rest they don't give the same. Alright, okay, let's try the next question. 18. Alkanes are known as paraffin hydrocarbons, and paraffin meaning a lack of affinity. Alright, so they are kind of unreactive. And one of the reasons why alkanes are unreactive, because the bonds between the carbon-carbon and carbon-H are actually like non-polar. Alright, no significant dipole moment means they're actually more or less non-polar. Actually slightly polar, but because carbon and hydrogen, the electronegativity difference is actually very small. Okay, so there isn't a real delta plus or real delta minus on the carbon or the hydrogen, right? So which means these carbon or these hydrogen, right, are not easily attacked by nucleophile or electrophile. So like for example, a halogenate alkane, if there's the Cl is very electronegative, so delta minus, delta plus. So halogenate alkane are very much more reactive because they will be easily attacked by what they call nucleophile, because the bond here is polar. Okay, but because alkanes, right? Okay, alkanes, right, they don't really have a polar bond, right? Which means actually these these carbon and hydrogen or what will not be easily attacked by nucleophiles or electrophiles, so they tend to be unreactive. Okay, so the answer is B. And yeah, and we know that the CH and CC bonds are relatively strong too. Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.